Hello world, this is the Computer Science Man, and today I'm going to start with the first lesson for AS level computer science. So before we start, I wanted to give a small introduction on my teaching methods. So what I'm basically going to do is follow the syllabus, and I've also jotted down some notes. So with that, I'm going to explain a topic to the best of my ability. And if you have any doubts, you can let me know in the comments. And so without further ado, let's get started. So the first topic we're going to start with today is showing understanding of different number systems. So that's the first topic we're going to start with. Right? So you probably know what number systems are from math. So you know how we use, day-to-day numbers, in math, right? In our daily life, we use it in everything. We use it in cooking, we use it in our schoolwork, we use it in, when we're playing video games. So that number system which we follow is known as the denary number system, otherwise known as the base 10, right? So what we follow is the denary number system. So this is the system we follow in our day-to-day lives. So you probably know how this works. So we have the units, right? So units as in the ones place, the tens place, the hundreds place, and the thousands place, right? This is what we were learned in elementary level math. And this is how we would represent a number based on its place values, right? So if we wanted to write the number 561, what we would do is we'll write, so 561, we would write the 5 in the 1 in the units place, the 6 in the tens place, because this is 60, right? This is 60 plus 1. So this is 6 into 10. So we will write this in the tens place, and this is 5 into 100. So right, so 5 into 100 plus 60 plus 60 plus 1. So we will write this here. So this is what we learned from the denary number system. But this is how we humans process numbers, whereas computers don't process it as denary. Otherwise, you probably heard the term binary being thrown out there. So this number system that computers follow is the binary number system, right? So this is what computers follow. They don't follow the system we follow, right? So in our system, we use the digits 0 to 9, and this is written in the terms of the powers of 10. So 1000 is 10 to the power 3, right? So 10 cube, 10 squared, and 10 to the power 1, and 10 to the power 0, right? So it's written in the powers of 10. That's why we call it a base 10 system, right? When you write the exponent, this is the base and this is the power. So this is the place power. So right, this is why we call it the base 10. That's because that's the base we write the power to. So likewise, for the binary system, it's known as the base 2. So here we have it in base 10, so 10 to the power something something. Here is 2 to the power. So how we can visualize this is that, so same thing here, right? So 2 to the power 0, 2 to the power 1, 2 squared, and 2 cubed. So we're going to start with 4 place values because that's the basic, not the most basic, but relatively basic thing we're going to start with. Okay, so you know what? I'll tell you some basic information about that. So in binary, one single digit, so one single digit is known as a bit. So if you write just 0, that's 1 bit. Or if you write just 1, that is 1 bit, right? So that is known as a bit. So here, if you can, you can count. So 1, 2, 3, 4. So we're writing this in 4 bits. Okay, we'll start with 4 bits. That's a commonly followed number of place values. Okay, so if we expand this as 8, 4, 2, 1. So now you may be wondering how we can use zeros and ones to represent, I don't know, a number such as 10, or you know what, not 10, we'll take 12. So how to represent a number such as 12? So in the denary system, what we have done is we need what's that, the tens place and the units place. So what we've done is we put 1 and 2, right? So this is for the denary number system, but for the denary system, we had the digits from 0 to 9, okay? But we don't have the digit 2. So like, how do we do it, right? So the simple thing is, so we have our 4-bit number here, which we have not filled out. You can think the 0 as an off, right? You can think that if it's like off switch, and you can think the 1 as an on switch. That means if I write 0, a value is represented, and if I write 1, sorry, if I write 0, a value is not represented. If I write 1, it is. So that's how binary works, right? So if you take 12, the easy way to convert this from denary to binary is simple, right? So so what do we have here? We have 12, right? So we go to the largest place value. Is the largest place value less than 12? So is 12 greater than 8? Basically, that's what we're saying in the reverse order. It is. So here we will write 1, okay? So why, I will get back onto that later. So 12 minus 8, so we can take the remainder. So we said, remember I said it's an on switch, so we're representing 8. 8, like a value of 8, we're representing up in 12. So the remaining is 4. So I would put, now I'll go to the next one. Sorry, it's greater than or equal to. So is 4 greater than or equal to 4? It is. So I'll put 1. And the rest I'll put 0. So in base 10, what we did is 10, 1, and 1, 2. So what we did is 10 into 1 less 2 into 1. And if you add this, you get 12. So the same thing follows for the binary system as well. So here you have 8, 4, 2, 1 instead of tens and ones and 100. So what you do is you do 8 into 1. So that 1 is the on switch. That means it represents a value. Plus 4 into 1 plus 2 into 0, which is 0, plus 1 into 0, which is also 0. So here you'll get 8 plus 4, which is indeed 12. Wow, it works, right? So 12, the denary number in binary 4-bit system, is represented as 1, 1, 0, 0. This is 12 in the binary form. Okay, so as far as you can see, basically how the denary system works, the same thing how the binary system works. But the only difference is here it's all in the powers of 2, and here it's all in the powers of 10, right? So if you understand that, you can basically convert any number from denary to binary. Well, if this method is a bit complex to you, there's also one more method. After I show you one more method, I will show you more examples, a few more examples. So another method you can follow is you can use the long division method by 2. So if you write 12, right? So if you write 12 and you divide it by 2, which is 6. So you get 6, right? So 12 divided by 2 is 6, and the remainder is 0. So right here, don't leave the first digit only, okay? Start from the next digit when you divide it, okay? So again, if you divide by 2, you'll get 3, right? And the remainder is again 0. And if you divide by 2 again, so we have to do successive division by 2, right? So if you divide by 2 again, the answer will be 1, but the remainder will be 1 as well. So again, if you divide it by 2, you will get 0, but the remainder will be 1. Then again, if you divide by, that's it. Yeah, then after that 0. So you have to, when you do successive division, you have to write the binary number from downwards to upwards. So basically like this. So if I write this here, 1 1 0 0. So here you get your number again. So you could follow the successive long division method by 2, or you can use the place values, and then you can compare your number, and based on that you can write 1 or 0, which is also on or off, which represents placeholder value. So and we'll try one more example. We'll try 13, right? So we're gonna try 13. So we're first to the place value method. So I'm gonna write my 4-bit number, right? So 13 is greater than or equal to 8. Yes, it is. So I'll put 1. 13 minus 8 is 5. 5 is greater than or equal to 4. So I'll put 1. So 5 minus 4 is 1. So is 1 greater than or equal to 2? No, it's not. So I'll put 0. So then is 1 is greater than or equal to 1? Yes, it is. So I'll put 1. So again, if you do 8 into 1 plus 4 into 1 plus 0, I'm just going to write this as 0 plus 1. You will get 8 plus 4 plus 1, which is 13. That's successful conversion. So next we're going to do the successive long division method as well. So I'm going to write 13, 2, 6. Again, remainder is 1. And what we need to do? 3, remainder is 0. Again, it's you divide by 2, you get the answer as 1. Remainder is 1. And again, you divide by 2. Quotient is 0, remainder is 1. Then, yeah, it's 0. So if you write this in from downwards to upwards order, you get 1, 1, 0, 1. And indeed, it's the same. So now you may be wondering if, okay, there's only 4 bits. Yes, it is true you can go above 4 bits. For example, you can go for 5 bits, 6 bits, or even more than 64 bits. Okay, you can go to like 64 bits. So for example, let's do till 8 bits. So what we did here is 2 to the power 0, 2 to the power 1, 2 squared, 2 cubed, 2 to the power 4, 2 to the power 5. Actually, 1 second. Okay, write this from the first. Okay, 2 to the power 0, 2 to the power 1, 2 squared, 2 cubed, 2 to the power 4, 2 to the power 5, 2 to the power 6, and 2 to the power 7. So since we're going from 0 to 7, this is 8 values. If you don't believe me, 1, 2, 3, 4, 5, 6, 7, 8. Yeah, since we're going from 0 to 7. So this basically transfers to 1, 2, 4, 8, 16, 32, 64, and 128. So if you want to remember the powers, you just double it. So 1 into 2, 2 into 2, 4 into 2, 8 into 2, yeah, just double. Right? So, okay, so back to 4 bits. So 8, 4, 2, 1. Let me ask you a question. What is the maximum denary value that we can store in this 4-bit system? So I'll give you a minute. Just pause the video and think. Okay, so what it will be is, so what I said was 1 is on and 0 is off, right? So if all these switches are on, that means it will have the maximum value. Like you can think it like that. So if I put 1, 1, 1, 1, that means none of the values will represent 0, right? So if I add this 8 into 1 plus 4 into 1 plus 2 into 1 plus 1 into 1, that means 8 plus 4 plus 2 plus 1, which is indeed 15. So the maximum number, denary number, you can represent in the 4-bit binary system is 15. Similarly, you can do this for, I don't know, you can do it for 5-bit, 6-bit, 7-bit, 8-bit, and so on and so forth. You just put 1 and add all the place values together. You get the maximum denary number you can store in this 4-bit or 8-bit number system. Right? So I hope you get the basics of conversion of binary and denary, and why computer, not why, the difference between binary, denary, and humans using linear and computers using binary. I hope you can differentiate that. In the next video, we'll talk about the prefixes. We'll talk about more binary addition, subtraction. We'll also go to further topics and more number systems such as hexadecimal, which is base 16. So I hope this video was helpful for you. To be honest, I was a bit nervous recording this. I'm gonna work on improving my I don't know, way of teaching so I can be more fluent and more helpful to you guys. So I'll see you next time. Thank you.